Everybody, Dr. A here, and in this video we're going to be exploring an example of how to compute a moment about an axis. So let's go ahead and get started. In the given information, we're being asked to compute the moment about the OA axis, and then we're being asked to express it as a Cartesian vector. So let's look at the 3D figure that we're given here. We see that we have a positive x-axis, we have a positive y-axis, and we see that we have the y-axis extending into the negative region, so that is the negative y-axis over here. And we have a positive z-axis. Now, the axis that we're trying to find the moment about is the OA axis. Now, this OA axis is a red line here that is in the YZ plane only. And we can tell that because it has a slope of a rise of 3 and a run of 4. And so you look at it as 4 feet along the positive y-axis and 3 feet up the positive z-axis, and that defines a point on that OA axis. So this is a planar axis, okay, in a single plane. Now, the force that's generating some kind of rotation around this axis is this force given to us here, which is already as expressed as a Cartesian vector. And that's going to be equal to 50I minus 20J plus 20K. And this Cartesian vector collectively has units of pounds. So that means you could write this as 50 pounds I minus 20 pounds J plus 20 pounds K. Now, where is this Cartesian vector force located? Well, its tail is at this point B here, which is a distance of positive 2 feet in the x direction, negative 1 feet in the y direction, and then positive 5 feet in the z direction. So this dotted line right here is the projected point of the tail of that vector, which is point B, down to the xy plane. Okay, so this would be a good time to maybe pause the video and sketch this out on your own paper and really take an extra minute or so to visualize what's going on here and what we have in this figure. Okay, so if we want to tackle this solution, what do? Well, we recall that whenever we have a three-dimensional force causing a rotation around an axis, we can calculate the moment about that axis as the unit vector of the axis, which I'm going to call U sub A, dotted with R cross F. So we still perform the R cross F operation, but we also execute the dot product operation with this, okay? So that gives us the magnitude of the moment about that axis A. Now, if you're a little rusty on this, go back and watch my background video on this, okay? So how do we know that this is the magnitude of the moment? Well, again, remember, when we perform the dot product specifically, when you dot two vectors together, you get a scalar. You get just a single number. So what's happening is we're first going to perform a cross product here, which will give us a Cartesian vector, and then we're dotting it with this unit vector, which will finally give us a scalar at the end of it. Now, the problem says express this as a Cartesian vector. So how do we express this moment magnitude as a Cartesian vector? Well, I'm going to put a comma here, and I'm going to say, well, if I just want the Cartesian vector of the moment about that A axis, I'm going to take that magnitude M sub A, and I'm just going to do a regular multiplication by UA. Okay, let me write that a little bit better. All right, and this will give me, oh, don't put those magnitude bars there. I don't know what I was thinking. That will give me the Cartesian vector MA, okay? So I accidentally put some magnitude bars here, which is, we already have the magnitude. This is the magnitude. So this is the Cartesian vector MA, okay? So that's ultimately what we're doing here, all right? Now, we got to figure out what all of these things are. Well, we already know the Cartesian force vectors F, okay? That's F. That's given to us up here. No problem, all right? What we need is the unit vector that defines that OA axis, and then we need a certain type of position vector. Let's get that unit vector that defines the A axis. I'm going to say U sub A, and we can get that by saying, well, that's just R sub A divided by the magnitude of R sub A. Okay, so we should be pretty familiar with how to do this at this point. This is a planar axis. We said it's in the YZ axis. So what we're going to do is say this is 4J plus 3K, and of course that's in units of feet. And then we're going to divide that by the magnitude. Let me draw that a little bit better for us. That's just 4 feet squared plus 3 feet squared, and you should get a unit vector of that A-axis of 0.8 J plus 0.6 K. Okay, so now we have that UA unit vector that defines the A-axis. So I'll put check marks there. Now, finally, what we need is a particular position vector, okay? Now, remember, what is this position vector R? Let's write this down. R is the position vector from what to what? That's the question. From what to what? From any point on the A-axis to any point on the line of action of F. Now, you might be thinking, well, Dr. A, you already wrote that down in the background video on this material. Yeah, I did, but I'm writing it down again because we want to make sure we really understand this. That position vector R can be a position vector from any point on this A-axis to any point on the vector F. So I could grab a point right here and then come all the way over here to the line of action of that vector, and I can use that as R. Now, what you would want to do is establish your position vector R based on convenient points, okay? So here's a question for you. What is a convenient point on the OA axis that I can use, and what is a convenient point on the line of action of this force vector that I can use? Well, a convenient point on the OA axis is just the origin, right? 0, 0, 0. So how about I use that? I mean, it's on the axis, so I can use that. And then a convenient point on the force vector that I can use is this point B at the tail, right? So how about I do that? How about I extend my position vector from O to B right there? I'll draw that a little bit better for us. O to B. And I use that as my position vector. No problem, no problem. So if I do that, I'm gonna color code here in yellow. R is just gonna be the position vector from O to B. And we take the coordinates of the second point, which is B, minus the coordinates of the origin, which is just 0, 0, 0. And so what are the coordinates of B? Well, we already said that, +2, -1, +5, okay? So I can write this position vector as 2I minus J, that's -1J, plus 5K. And of course, that's going to carry units of feet. So now I have everything I need. I can check this position vector R off, okay? So how am I going to evaluate the magnitude of this moment about the A-axis? Well, I'm going to use a 3x3 determinant. So if you're a little rusty on this, go back and look at the background video. MA is going to be this 3x3 determinant. The top row is going to be made up of the components of UA, all right? So we're going to have UAX, UAY, UAZ. The second row are the components of R, so RX, RY, RZ. And remember, these R components, that's of the ROB that we just got. And then the third row is going to be fx, fy, fz. All right. So for us, substituting in these values, what do we have? We're going to have 0, 0.8, 0.6. Then we're going to have 2 feet, -1 foot, and 5 feet. And then we're going to have the components of this vector, 50, -20, and 20 pounds. So 50 pounds, -20 pounds, and 20 pounds. Now, this is a 3x3 determinant, so how do I evaluate this? Well, remember, we recopy the first two columns over here, right? So I can recopy these and say 0, 0.8, 2 feet, -1 foot, 50 pounds, -20 pounds, and then I perform some diagonal multiplications. So that's going to give me a 0 because I got 0 times -1 times 20. I'm going to perform this double multiplication here. That should give me 200 pound-feet. Then I'm going to perform this multiplication here. That should give me minus 24 pound-feet. And then I'm going to multiply diagonally upwards, but I'm going to negate that. So I'm going to put a negative, open parentheses. That'll give me, that first value will give me a -30 pounds. Here's another 0. And then here is a positive 32 pounds. And remember, this negative gets distributed to both of these terms. And so finally, when I combine everything, maybe pause the video so you can make sure you get the same thing I get. When I combine all these values in green together, I add them all up, distributing this negative between these two values, I'll get 174 pound-feet, okay? Now, that's the magnitude of the moment about the axis, the OA axis. I needed this as a Cartesian vector, though. That's what the second sentence of the problem statement said. So as a Cartesian vector, what I do is I take the magnitude MA times the unit vector U sub A. And so I'm going to say 174 pound-feet multiplied by that unit vector, which is right here. So that'll be times 0.8J plus 0.6K. All right. And when I distribute this to each of these components, this is a vector times a scalar. What do I get? I get 139J plus 104K, collectively with units of pound-feet. And this is my final answer. So hopefully you found this example helpful to you. If you did, please hit like and subscribe. And don't forget to be on the lookout for other content like this. Thanks for watching.